Hello, my name is Rolf Westerteiger from Math to Market, and in this presentation I want to give you several reasons why you might want to run geodetic computations in the cloud and offer you 3 different possible solutions to do so, depending on your application scenario. Let's highlight some of the issues that the cloud can help solve by looking at some quotes from our clients. One division manager told us that their upper management asked them to minimize their local hardware deployment, which refers to workstations and servers, so basically keep only a laptop per employee. One engineer told us that their average turnaround time to design a new product currently is 12 months, and their management asked them to reduce it to 3 months. Another head of R&D said that they need to improve their CO2 balance and therefore they need to outsource their IT infrastructure. Let's look at the following figures as an example how the cloud can speed up a material development project. This was a project that we did with a customer. Unfortunately, I cannot share any details, but it required 24 individual simulations, each on 48 CPU cores and 348 GB of RAM. Each simulation ran on a processed synchrotron sample with 2400 by 2400 by 2100 voxels. And using the cloud, the simulations finished in just 29 hours instead of the 3 weeks that would have been necessary running sequentially on a local machine. Before diving into the different solutions that we can offer you, let me give you a quick rundown of the different abstraction levels that you can encounter when dealing with cloud solutions. First of all, we have on-site, on-premises deployment. In this case, the customer owns and maintains local hardware, so there's no cloud involved at all. This is basically, if you will, classical computing. Next, we have infrastructure as a service, or called IaaS. Here, a customer explicitly starts virtual machines in the cloud, maintains the operating system and the application software running on these machines. And the next abstraction level then is platform as a service, PaaS. Here, the individual machines are abstracted away. The customer basically uploads applications and the cloud provider handles the execution and scaling automatically. For example, the cloud provider automatically starts additional machines to run your jobs if more computing power is needed. And last but not least, we have software as a service. There, a specific application is maintained in the cloud by a third-party provider, and the customer can use it remotely, very often via a web interface. Now let's talk about the different options that we have to run Geodict in the cloud. First of all, we have a web-based interactive remote session. This is a software as a service solution. Second, we have web-based GeoCloud batch operation. This is a platform as a service. And last but not least, we have a simplification of the second step by integrating it into the Geodict GUI. This still is a platform as a service solution, but it's also an on-site solution because in this case you still need a local Geodict instance. The first solution I want to present you is the web-based interactive remote session, which gives you a full Geodict user interface within your web browser. We currently have a deployment on Amazon Web Services, but we would happily support Azure or Google Cloud as well. In terms of data exchange, you can up and download your data using SFTP, which is for example implemented by WinSCP on Windows, or you can mount your OneDrive, Dropbox or similar cloud drive as well. In terms of data security, the session is encrypted via HTTPS, file transfer is encrypted via SFTP, and the ephemeral storage of the virtual machine is encrypted using a random single-use passphrase which is generated during boot time. Once the machine shuts down, this passphrase is forgotten. You can freely choose the cloud region where the instance is going to be started depending on your company's demands. For example, we can start instances in the Frankfurt region of Amazon Web Services. By using this solution, you can reduce your IT investments and labor costs for acquisition and maintenance of workstations and computation servers. And of course, you can scale your computing resources as needed, as you can always start more instances. To give you a symbolic overview of how it works, here we can see the cloud, for example, Amazon Web Services, where a virtual machine is running a Geodict instance. And this Geodict instance has a license which talks to a license server. And you as a user interact via your web browser with that Geodict user interface. And you also interact with the virtual machine by exchanging files, either via SFTP directly or via cloud storage, for example by placing a file on your Dropbox and accessing it from the virtual machine and vice versa. Now let me show you how easy it is to use Geodict interactively in the cloud. I've opened my web browser and I have a bookmark here, which leads me to the front end. And here you can see that there are currently no cloud instances running. And once I click on the button Start Instance, it will start an instance in the Amazon cloud. We'll wait a little bit, then the instance should appear in the table. And it'll take another 1 or 2 minutes for the instance to actually come up and be reachable. You can here see the instance ID, the type of machine, which is an Amazon specification for this type of machine, which has 16 cores and 128 gigabytes of RAM. You can see the IP address, and you can see the randomly assigned password when you click the Show button here. And this password you can then mark and copy to your clipboard because you're going to need it later. And now I will fast forward for a bit. After a few minutes, we can click the Connect button here. And then we are greeted with this new tab in the browser, which connects us directly to the machine. Remember that we have copied the password from the first tab. Now we click on Connect here in the center of the screen and just paste the password here. And then we are greeted with a Linux desktop. On the left-hand side, we can make this larger. Make it fill our screen. And now we can start Geodict directly from the desktop. And now we just have a regular Geodict installation that we can use freely, basically. Now, in order to have something to work with, let's upload a structure to this virtual machine instance. So I will go back to my desktop and I will start WinSCP. And here I will connect with a virtual machine. I've already entered this here. As you can see in the browser, tab here, the machine is called vnc1.maththemarket.de. And you can just connect to this machine with an SFTP client such as WinSCP using the username Geodict and the password that we gave you earlier. So I'll just paste this password again here. And now I'm connected. And as you can see, I have a My First Geodict project folder on the remote machine. This is actually currently this is a 1 terabyte drive on the remote machine that you can basically freely use to store your structures and your simulation results, and later download your results from there as well. And I will go to my first Geodict project on my local machine here, and there I already have a structure which is the Berea sandstone, and I will just drag and drop this over here to upload it. And now the file is on the remote machine. And I can go back to the tab here, go back and make it full screen. Next, I will load the structure that I've uploaded. I go to File, Open Structure, select the file. And as you can see, this is actually interactively usable with no problem. So it's almost as working in a local environment. Now next I will go and run a flow simulation on this. Go to Predict, FlowDict, select the Lear solver and click Run. And now I will fast forward this a bit. The simulation is done and we see the usual GDR result viewer, and of course we can go and load the flow fields and just load them all. And close the result viewer. And now to make the visualization a bit nicer, I will just clip into the structure a little bit and change the transparency settings of the volume field. Maybe like this. Apply it. And we can see that we get a nice visualization of the flow field distribution. And now we can go and save this image if we want to. Of course, we could also save videos as well, but let's just save an image. Go to File, Save Image As. And I just save it as sandstone.png. And then let's just go back to our local machine. I'll open WinSCP again. And I will refresh this remote folder here. And as you can see, all the results that we've generated are here. So the Lear-Stokes result GDR and the subfolder with the volume fields and the image that we created. So for example, let's say we just want the GDR file and the Sandstone PNG on our local machine. I'll just move this over here. And now I'll go and open a local copy of Geodict on my local machine. And here I can now go to File, Open Results, and open the file that I've just copied from the remote machine. And look at all the GDR data. Of course, I cannot open the flow fields here. If I had copied them, I could also open them on my local machine. But here I can, for example, look at the layered pressure plots, etc. And that's basically it. Next, I want to talk about the GeoCloud batch operation interface, which is also web-based, but in contrast to the previous solution, here you do not interact with the remote Geodict instance directly, but instead you submit bundled computation jobs for the GeoCloud to execute on some Geodict instance and return the results to you. This option has many of the advantages of the previous solution, but one of the differences is that it requires a basic understanding of GeoPython scripting, as you will see. It rewards that, however, by the ability of running massively parallel computations, for example case studies or running simulations on many different CT datasets at the same time. It is based exclusively on the Google Cloud platform and the servers are located in Europe. Here again we have a cloud which executes Geodict instances, but in this case it's a little bit more abstract because you do not talk directly to these machines running Geodict. Instead, what you do is you prepare your data, prepare a GeoPython script, zip it up and upload it to a web interface. And using this web interface, you can determine that your job should be executed on a certain type of machine. This web interface will then take care of that execution, and the result data from that execution will then be made available for you to download once the job is completed.
Here we create an example for a parameter study in the GeoCloud using the KaleidoScript. We select the KaleidoScript, and in the KaleidoScript we select a Geodict macro. We choose the number of machines and select the license we want to use. Our Geodict macro performs structure generation and flow simulation on the structure. The solid volume percentage is the parameter we vary in the study. The KaleidoScript creates the simulation cases ready for upload. Here we see the 8 cases the KaleidoScript has created automatically. After this, we log in at geodict.kaleidosim.com. Here we add a new project. Select the project name and the Geodict version. After that, we create the simulation case. And we have the option to select different machines. Also with GPU, so here we can select different GPU types and number of GPUs, for example for AI training. After selecting the cores of the machine, we upload our simulation cases. So in this case, we created 8 runs. We want to run in the cloud in parallel. And we create the case. Here we can select all 8 runs and start the simulation in parallel on 8 parallel machines. After the simulations are completed, we can simply download all results or selected results for all 8 simulation cases.
The pricing model is based on a currency, if you will, called a virtual CPU hour. Whereas a standard machine with 8 cores will consume 8 vCPU hours per hour, and a machine with more cores will consume proportionally more. Machines which have additional hardware, for example more RAM or a GPU, can have additional factors applied on top of the core count. The payment scheme is based on a prepaid model where you make an upfront payment to a cloud account from which the vCPU hours that your jobs consume are then deducted, which of course is good for cost control. But we can also negotiate a pay-per-use model. Licensing is based on bring your own license, which means that your existing Geodict license will be mirrored for the cloud, which means you get a cloud exclusive license which has the same modules that you have already licensed but with unlimited process counts, and beyond that there are no additional licensing costs. Finally, I want to talk about a solution which is currently in development targeting Geodict 2023, which is the logical next step of the previous approach that I showed you, namely integrating this web-based batch operation directly into the Geodict user interface. This is a component of the GeoCloud Eurostars project, which is a collaboration between Math2Market, the Zürcher Hochschule für Angewandte Wissenschaften, and KaleidoSim, which is the cloud provider behind the previously demonstrated solution. The project starts this month, and the goals are, besides integrating the GeoCloud into the Geodict interface, to enable AI training and AI usage in the GeoCloud using GPUs, and to develop cloud apps to exploit massively parallel AI-driven inverse engineering, which includes forward prediction of effective properties from structure without using solvers, and the inverse operation of predicting structure generator parameters from effective properties. Namely, if you have given physical property to find, for example, the fiber geoparameters to generate fiber structures which have exactly this property. Now, in contrast to the previous diagram, you can see that the web user interface is gone here. This is because the Geodict instance now talks directly to the GeoCloud. In practice, this means that, for example, if you have loaded a structure and you go to Flowdict, and usually you would click Run to run the simulation locally, you would have an additional button, Run in Cloud, which instead packs this structure and the instructions required to run Flowdict, uploads them to the GeoCloud, starts the execution, and gives you a chance to download the results once they're ready. Furthermore, if you have a GeoPython macro recorded, you can also upload this whole macro to the cloud and run all of it in a cloud instance as well, and get all the results back in one zip file. In summary, I have presented three different approaches of running Geodict in the cloud. First, we have the web-based interactive remote session, which is great for pre-processing, for example, running import geo on your CT scans, for visualization, and for working with large datasets in general, which your local machine might not be able to handle. You can choose to either analyze results directly on the remote machine or download them and open them locally. The pricing is based on the cost of Amazon Web Services plus a pay-per-use Geodict license. Next, we have the GeoCloud batch interface, which is provided by KaleidoSim. This is great for parallel batch operations, for example, case studies or running simulations on many different structures. And the pricing here is based on bring your own license and prepaid or pay-per-use pricing based on a vCPU hours model. Last, I gave you an outlook to what we internally call the Cloud button, which means integrating the GeoCloud batch interface directly in the Geodict user interface. This is a feature which is in development for Geodict 2023, and it's based on the KaleidoSim Cloud as well. With this, I want to conclude my presentation, and I'll be happy to take your questions. Thank you for your attention.